Welcome to this quiet corner of thought, where we let curiosity settle like dust and give wonder permission to unfold slowly, naturally, without rush or urgency. Tonight we're not chasing headlines or seeking grand revelations that will change everything you thought you knew. Instead, we're doing something different, something that requires patience and a willingness to sit with uncertainty. We're asking a question that sounds deceptively simple, but opens into realms of vast complexity and profound mystery. What if we're not the first? Not the first civilization to rise on this planet. Not the first minds to look up at the stars scattered across the night sky and wonder what they are, what they mean, whether anyone else is out there looking back. Not the first hands to deliberately shape the world around us with intention and foresight and accumulated knowledge. What if, long before our species took its first uncertain steps on the African savanna, long before the first pyramid was raised stone by stone under the Egyptian sun, long before the first fire was deliberately kindled and tended and understood, someone else was here? This isn't a conversation about ancient aliens visiting from distant star systems. This isn't about mythical lost continents like Atlantis, woven from imagination and wishful thinking. This is about something potentially more unsettling and more profound. The possibility of something homegrown, something that emerged from Earth's own evolutionary processes, something biological and terrestrial and native to this world. Something that evolved here, lived here, perhaps even thrived here for a time, and then disappeared so completely, so thoroughly, that the planet itself may have forgotten it ever existed. It's a thought that sits at the intersection of multiple disciplines: geology with its patient reading of rock layers, biology with its understanding of how life evolves and adapts, chemistry with its analysis of molecular signatures, and something harder to name, a kind of existential archaeology that asks not just what happened, but what could have happened, what might have happened in the vast stretches of time before we arrived, and whether we would even recognize the evidence if it existed. The question might sound like science fiction, and in many ways it does share that genre's willingness to imagine beyond the comfortable boundaries of what we're absolutely certain about. Science fiction has always excelled at asking what-if questions that push against the edges of known reality. But this particular question is also a legitimate scientific inquiry, one that's been discussed in peer-reviewed academic papers, debated at geology conferences, and explored by researchers who take it seriously, not because they believe ancient civilizations definitely existed, but because asking the question tests our understanding of how evidence survives, how we interpret the geological record, and what we might be missing. The core of the inquiry is elegantly simple yet profoundly challenging. If an advanced civilization had existed millions of years ago, long before humans, long before our primate ancestors, long before anything resembling our lineage existed, would any trace of it survive the immense geological forces that constantly reshape our planet? Would we be able to detect it? Or would everything they built, every tool they manufactured, every structure they raised, every thought they preserved, every achievement they accomplished, be ground back into rock and sediment and dust until it became completely indistinguishable from the natural background, from the ordinary processes of planetary evolution? Before we venture deeper into these questions, before we descend into the genuine depths of geological time, I want to take a moment to acknowledge you, wherever you are right now in this vast world. Maybe you're lying in bed as darkness settles outside your window, watching shadows lengthen across walls, feeling the day's concerns beginning to recede. Maybe you're watching dawn break over unfamiliar horizons, the first light touching landscapes you're only beginning to know. Maybe you're in that peculiar in-between time, that liminal space where the world feels suspended and thoughts can wander freely without the usual constraints of schedules and obligations and the endless demands of daily life. The subject we're exploring tonight is fundamentally about ancient things, about spans of time so vast they make all of human history look like a single breath, a momentary exhalation in the long life of the planet. And yet here we are, you and I, connected across space and time by this strange and wonderful medium of sound and story and shared curiosity. There's something genuinely profound in that connection, something that mirrors what we're investigating. The idea that minds reach across voids to touch one another, to share thoughts and questions and wonder, even when separated by unimaginable distances or vast expanses of time. If you find this kind of slow, deep questioning compelling, if you're drawn to ideas that don't rush headlong toward neat conclusions, but instead circle around mysteries with patience and care, then perhaps you'll want to help this conversation reach others like you, other curious minds who find value in sitting with big questions. A simple gesture, a like or subscription, helps these quiet investigations find their way to people who appreciate them, who are hungry for this kind of thoughtful exploration. But there's no pressure here, no urgency, no obligation. Just an invitation, like a faint trail visible in the forest that might lead somewhere unexpected if you choose to follow it, or might simply be worth walking for its own sake. So settle in now. Find a comfortable position, whatever that means for you. Let your breathing slow down naturally without forcing it, just allowing it to find its own rhythm. Let the concerns of your day begin to recede like tide pulling away from shore, leaving behind only the things that truly matter. We're going to take a journey backward, not through human history with its wars and empires and revolutions, but through something much larger, something that puts human concerns into a perspective that can be simultaneously humbling and liberating. We're going to descend through layers of time so deep that our entire species becomes a thin line near the surface, barely visible in the grand scheme of things. We're going to look at how the Earth erases evidence through processes that operate with patient inevitability over millions and billions of years. We're going to examine how continents move across the globe like pieces on an unimaginably slow chessboard, how mountains rise and crumble, how oceans open and close, how the very ground beneath our feet is temporary, transient, constantly being recycled and renewed. Because before we can meaningfully ask whether someone came before us, we need to understand just how good this planet is at wiping the slate clean, at erasing the past, at forgetting. The Earth is old, not just old in the way a historic building or an ancient tree is old, not just old in the way that feels distant to us but still comprehensible. The Earth is old in a way that almost defies human comprehension, old on a scale that makes our intuitions fail. About 4.5 billion years old, give or take a few 100 million years, which itself is a span of time longer than all of human existence. 4.5 billion years. Say that number slowly and try to feel its weight. 4,500 million years. Each one of those years containing 365 days. Each day containing 24 hours. Each hour containing experiences, changes, processes, transformations. For the vast majority of that incomprehensible span of time, there were no humans. We are an extraordinarily recent arrival. For most of Earth's history, there weren't even mammals walking around. For much of it, there was no life on land at all, just empty continents worn by wind and rain and the slow work of geological forces. Life spent billions of years confined to the oceans, evolving in microscopic forms, single-celled organisms dividing and adapting, and gradually, infinitesimally slowly, building the chemical and biological foundations that would eventually, after unimaginable spans of time, allow complex organisms to emerge. And yet, despite how empty that might sound, despite how barren and lifeless most of Earth's history was, this was when the vast majority of the planet's story was written. Every mountain range that has ever existed, every ocean that has opened and closed like a vast slow-motion tide, every continent that has drifted across the globe, colliding and separating and colliding again, all of this happened during that vast stretch of time when nothing resembling human intelligence existed, when there was no one to witness it, to record it, to wonder about it. The planet was active, dynamic, constantly reshaping itself through processes that operate on timescales we can barely comprehend even when we study them. Plate tectonics moving continents millimeters per year, which doesn't sound like much until you multiply those millimeters by millions of years and realize entire ocean basins can open and close. Erosion removing mountains grain by grain, which seems impossibly slow until you understand that given enough time, enough millions of years, even the tallest peaks are ground down to nothing. Volcanism bringing new rock to the surface, while subduction zones drag old rock back into the planet's interior to be melted and recycled. And throughout all of this vast activity, throughout all this time, the Earth was writing its history in layers of rock and sediment, in the chemical composition of minerals, in the arrangements of crystals and the distributions of elements. But that history is fragmentary at best, incomplete, often illegible, like a book that's been torn apart and burned and scattered and buried, with only random pages surviving in damaged, water-stained, barely readable condition. The planet doesn't keep a diary in any conventional sense that we might recognize. It doesn't carefully preserve everything that happens equally. It doesn't maintain archives or libraries or organized records. Some materials last longer than others, persisting for millions of years under the right conditions. Some environments are better at preservation than others, offering protection from the destructive forces that would otherwise erase everything. And fundamentally, the basic processes of geology are constantly working against the survival of any evidence, constantly recycling and renewing and erasing. Wood, unless it's in an exceptional environment like a peat bog or a very dry cave or frozen in permafrost, decays within years or decades, broken down by fungi and bacteria and insects into simpler compounds that disperse and disappear. Metal, despite our intuition that it's permanent, oxidizes and corrodes and crumbles, especially when exposed to oxygen and moisture, returning to forms not very different from the ores it was originally extracted from. Bones, which seem durable, dissolve in acidic soils, their minerals leaching away until nothing remains but perhaps a faint stain in the sediment. Even stone, which we think of as the very definition of permanent, gradually weathers away grain by grain, molecule by molecule, worn down by wind and water, and the slow chemical processes that break down even the hardest rock. And time doesn't just pass neutrally, like a river flowing past without affecting the banks. Time is an active force, an agent of change and destruction and transformation. It buries things under accumulating layers of sediment that build up slowly but inexorably. It melts things when tectonic plates dive back into the Earth's mantle in subduction zones, dragging whatever was on the surface down into regions where temperatures and pressures are so extreme that rock becomes plastic and flows like thick honey. It crushes things under the weight of overlying rock as sediments accumulate and compress. It shifts and folds and faults and erases through countless cycles of creation and destruction, through processes that repeat over and over again on timescales that dwarf human history. Mountains that seem eternal to us, that seem like permanent fixtures of the landscape, are actually temporary features in geological terms, rising through tectonic collisions when continents crash into each other and then slowly, inexorably crumbling through erosion, their material washed away to accumulate elsewhere. The Himalayas, those magnificent peaks that seem timeless, are actually young mountains in geological terms, still rising as India continues to push into Asia, and already beginning to erode away even as they rise. In 100 million years, they'll likely be gone, worn down to low hills or flat plains, their material distributed across vast areas. Oceans open and close over hundreds of millions of years in a process geologists call the Wilson cycle, named after the Canadian geologist who first described it. Continents drift apart, new ocean floor forms between them, the ocean widens, and then eventually the process reverses. The ocean begins to close as subduction zones form. Continents drift back together and eventually collide. The ocean completely disappearing, its floor entirely subducted and melted, leaving almost no trace of its former existence. The Atlantic Ocean, which now separates the Americas from Europe and Africa, is actually a relatively young ocean, having opened only about 180 million years ago when the supercontinent Pangaea began to break apart. Before that, there was no Atlantic, and eventually, in the deep future, it will likely close again as the continents continue their slow dance. The face of the Earth has been completely rearranged many times over in its long history. What was once ocean floor might now be high mountain peaks, the seafloor sediments folded and lifted into ranges like the Himalayas or the Alps, fossils of marine organisms now found at elevations where the air is thin and cold. What was once a tropical coastline might now be buried under miles of ice at the poles, or submerged beneath deep ocean waters, or thrust up into mountains, or completely erased through subduction. Every few 100 million years, the entire configuration of continents changes dramatically enough that the planet would be essentially unrecognizable, the maps completely redrawn. When you look at Earth's history this way, with this geological perspective that encompasses billions of years, it becomes clear that the absence of evidence for things that happened long ago isn't surprising at all. What's genuinely surprising, what should actually astonish us, is that any evidence survives at all. For anything to last more than a few million years is already an extraordinary event, an exceptional occurrence requiring a very specific and fortunate combination of circumstances. It needs to be buried quickly, protected from weathering and biological decay before those processes can destroy it. It needs to be buried in the right kind of sediment that will preserve rather than destroy, that will protect rather than corrode. It needs to avoid being heated or compressed so much that its original form is lost or transformed beyond recognition. And then, after surviving for millions of years in this preserved state, it needs to be exposed again through erosion or human excavation at exactly the right moment so that someone can actually find it before it's destroyed by weathering. Now let's engage more deeply in a thought experiment, an exercise in imagination grounded in what we know about geology and biology and the processes that shape our world. Imagine that 100 million years ago, deep in the age of dinosaurs, during what geologists call the Cretaceous period, an intelligent species evolved. Not necessarily descended from dinosaurs, though that's one possibility. Maybe it was some other lineage entirely, something we know nothing about because it left no traces we've recognized. Maybe it was bipedal, walking upright like we do. Maybe it wasn't. Maybe it lived on land, building structures and developing agriculture. Maybe it lived primarily in the oceans, a marine civilization we can barely imagine. Maybe it moved between both environments, equally at home on land and in water. Maybe it didn't build with stone or metal at all, using materials we wouldn't even recognize as technology, working with biological systems or chemical processes or principles we haven't discovered yet. Maybe this species developed what we might call culture or society, though those terms are loaded with our own assumptions and biases. Maybe it had language, methods of communication that allowed complex ideas to be shared between individuals and across generations. Maybe it had art, expressions of beauty or meaning that went beyond pure utility. Maybe it had social structures, hierarchies, or cooperation, or ways of organizing collective action. Maybe it had ways of passing knowledge between generations, oral traditions or symbolic markings, or methods we can't even conceive of. And then, for whatever reason, after existing for thousands or perhaps millions of years, it disappeared. Perhaps there was a catastrophe, sudden and devastating, an asteroid impact like the one that would later end the age of dinosaurs, throwing dust into the atmosphere and disrupting climate. Systems worldwide. Massive volcanic eruptions releasing enormous quantities of gases and ash, poisoning the air and blocking sunlight. Rapid climate change making the world uninhabitable for species adapted to previous conditions. Perhaps there was conflict, warfare, the civilization destroying itself through violence or through technologies that spiraled beyond their control. Perhaps there was gradual resource depletion, soils worn out through intensive agriculture, forests cleared beyond recovery, key species driven to extinction, the complex web of ecological relationships unraveling. Or perhaps it simply faded away over time, populations declining for reasons we might never understand, knowledge being lost as death rates exceeded birth rates, until nothing remained but empty ruins that would themselves erode away. If this scenario had actually occurred, if something like this had genuinely happened 100 million years ago, and we arrived now asking whether we could detect it, asking what evidence might remain, what would we find? Here's the uncomfortable truth, the thing that should give us pause and make us question our assumptions. We might find absolutely nothing at all. We might search with our best technology, our most sensitive instruments, our most sophisticated theories, and still find no trace whatsoever. We're not as permanent as we like to think. Our cities, our infrastructure, our monuments, none of it is built to survive geological time. Leave a modern city completely alone, with no human maintenance, for just a few centuries, and nature begins to reclaim it aggressively, enthusiastically. Within a few thousand years, a blink in geological terms, it becomes difficult to recognize what was once there. The buildings collapsed or overgrown, the streets broken and covered with vegetation. But a few million years, at that immense timescale, erosion and tectonic activity will have completely transformed the surface. What was once land might now be ocean floor, subducted beneath a continental plate. What was once a mountain might be a flat plain covered with sediment. What was once a river valley might be uplifted into highlands, and most traces of anything built on that dynamic, changing surface will be gone entirely, completely erased. This isn't science fiction or wild speculation. It's based directly and carefully on what we know from geology and archaeology, from decades of studying how evidence survives and how it's destroyed. Even traces of recent prehistoric human activity, things that happened just thousands of years ago, are incredibly rare and difficult to find, requiring specialized techniques and often depending on pure luck. Not because humans weren't active, not because they didn't do significant things, but because the Earth is a remarkably efficient recycler of materials, constantly breaking down and reusing everything. Consider the fossil record that we use to understand ancient life, to reconstruct ecosystems and evolutionary processes and the history of life on Earth. It's incredibly spotty and incomplete, riddled with gaps that span millions of years, not because ancient life wasn't abundant or diverse, but because the conditions required for fossilization are very specific, unusual, and rare. Most organisms that die are never fossilized. Never. They're eaten by scavengers who scatter the remains. They decompose, broken down by bacteria and fungi and insects into simple compounds that disperse into the environment. They dissolve in acidic soils, or are crushed by geological forces, or are destroyed by heat, or simply vanish without a trace. To become a fossil, to have even a chance of being preserved in rock for millions of years, requires an extraordinary chain of unlikely events all occurring in the right sequence. First, rapid burial before decay destroys the body, before scavengers scatter the bones, before the elements break everything down. This usually requires sudden events: a flood that buries remains in sediment, a volcanic eruption that covers everything in ash, a landslide that seals remains away from oxygen and organisms. Then there needs to be replacement of organic material with minerals, through groundwater percolating through the sediment, gradually replacing the original biological molecules with stone while hopefully preserving the shape and structure. Then protection from erosion and tectonic forces for millions of years, which requires geological stability that's actually quite rare. And then finally, the extraordinary luck of that fossil-bearing rock being exposed at the surface where someone can find it, but exposed recently enough that weathering hasn't already destroyed it. Multiply that challenge by tens of millions of years. Multiply it by the complete transformation of landscapes through tectonic activity, and you start to see the true scale of the problem we're facing when we ask about ancient civilizations. And it's not just organic remains like bones and shells that are difficult to preserve. Buildings, artifacts, tools, manufactured objects, even those made of supposedly durable materials like stone or metal, don't last forever in geological terms. Most metals corrode within thousands of years when exposed to oxygen and moisture, essentially returning to the oxidized ores they were originally extracted from. Bronze, iron, steel, all corrode and crumble. Even gold, which resists oxidation, can be dispersed through geological processes. Plastics break down, especially when exposed to ultraviolet light from the sun and to microbial action, fragmenting into smaller and smaller pieces. Even concrete, that ubiquitous material of modern construction that seems so permanent, eventually crumbles when left without maintenance as water seeps into tiny cracks, freezes and expands, and gradually breaks it apart. Steel reinforcing bars inside concrete expand as they rust, creating internal stresses that crack the concrete from within. So if a civilization had existed in the truly distant past, especially one that didn't leave behind vast quantities of stone structures like pyramids or monuments carved from solid rock, we might genuinely have no way of knowing it ever existed. The question isn't whether they tried to be remembered. The question is whether the Earth would allow them to be remembered, whether anything could possibly survive the relentless recycling, the constant transformation, the inexorable processes that grind everything down and build it up again in new forms. And the answer, the honest scientific answer based on everything we know about how the planet works, is that very little survives, and what does survive often does so only by accident, only through fortunate combinations of circumstances that protected it from the forces that destroy everything else. Think about what we know of human prehistory, of the period before written records, before agriculture, before settled civilizations. We have stone tools, sometimes in great quantities, because stone is durable. We have occasional bones that happen to be buried in the right conditions. We have cave paintings in locations where they were protected from weathering. We have very little else. We don't have their languages except as reconstructed guesses. We don't have their music except as speculation based on ancient instruments. We don't have their stories except as dim echoes in myths that may or may not preserve genuine memories. We don't have their thoughts, their dreams, their fears, their hopes, their detailed understanding of their world. And this is for our own species, for humans, for remains that are only thousands or tens of thousands of years old, not millions. If we have this much trouble reconstructing the lives of our own ancestors from such recent times, how could we possibly expect to find clear evidence of a completely different species that lived millions of years earlier? The honest answer is that we probably couldn't, not unless they left something truly exceptional, something that managed to survive against all odds. You might reasonably wonder at this point, and you should wonder, whether anyone has seriously considered this idea from a rigorous scientific perspective. whether this is just idle speculation or whether actual working scientists have thought about it carefully. And the answer is yes, absolutely, serious researchers have engaged with this question. In 2018, two respected scientists with impressive credentials published a fascinating paper exploring precisely this question in a peer-reviewed scientific journal. Gavin Schmidt, who directs NASA's Goddard Institute for Space Studies, one of the world's leading climate research centers, and Adam Frank, an astrophysicist at the University of Rochester with expertise in the evolution of planets and civilizations, co-authored a paper that asked a deceptively simple but profoundly important question. They weren't proposing that an ancient pre-human civilization actually existed. They weren't claiming to have found evidence of ancient cities or technology. Instead, they were asking something more subtle, more methodological, more scientifically useful. If such a civilization had existed, how would we even detect it? What kinds of evidence should we look for? What traces might persist for millions of years? And might such traces already exist, sitting in our geological data, misinterpreted as natural phenomena or simply overlooked because we weren't asking the right questions? They called their thought experiment the Silurian hypothesis, a somewhat tongue-in-cheek reference that science fiction fans might recognize. It's named after a race of intelligent reptilian beings from the long-running British science fiction series Doctor Who, supposedly an ancient civilization that evolved on Earth long before humans. The name is playful, but the scientific question they were raising was entirely serious, entirely rigorous, entirely worth investigating. They wanted to explore what traces an industrial civilization would leave in the geological record after millions of years had passed, and whether such traces might already exist in the data we've collected but not properly recognized or interpreted. Their approach was clever, innovative, and grounded in solid geochemistry. Instead of looking for traditional artifacts like buildings or tools or written records, which they acknowledged were extremely unlikely to survive deep time, they focused on chemical signatures and anomalies, on changes to the planet's chemistry that might persist even when physical structures have been completely erased. What kinds of markers would an industrial civilization leave behind that might last for millions of years? What would be the most durable evidence of technological activity? They considered things like carbon isotope ratios, the relative abundance of different carbon isotopes, which change in characteristic ways when large quantities of fossil fuels are burned, because fossil fuels have distinctive isotopic signatures different from other carbon sources. They looked at unusual concentrations of rare elements, particular patterns in the distribution of metals and minerals that might indicate mining and refining activities, industrial processes that concentrate particular elements in ways nature rarely does. They considered synthetic molecules, artificial chemical compounds that don't occur naturally through any known geological or biological process, substances that might resist chemical breakdown for long periods under the right conditions. In other words, they were thinking like detectives who can't find a body, can't find a weapon, can't find any traditional physical evidence, but are hoping the chemical traces might still tell a story, might preserve information even when everything else has vanished. They were asking what a civilization looks like when filtered through millions of years of geological processing, when everything obvious has been erased, but subtle chemical fingerprints might remain. This approach raised an uncomfortable possibility that goes directly to the heart of our inquiry, that should make us pause and reconsider our assumptions about the completeness of our knowledge. Maybe the absence of obvious evidence, the fact that we haven't found ancient cities or tools or clear signs of pre-human civilization, isn't actually evidence that nothing was there. Maybe it's simply what things look like when a planet systematically resets its surface every few 100 million years through plate tectonics and erosion. Maybe absence of evidence genuinely isn't evidence of absence, at least not when we're dealing with timescales this vast. because civilizations don't vanish cleanly, don't disappear without affecting their environment. They leave impacts, fingerprints, traces of their activities. Energy use requires resources and produces waste products. Agriculture changes soil chemistry and alters erosion patterns. Mining extracts and concentrates particular elements. Manufacturing produces byproducts and transforms materials. All of these activities change the chemical composition of the environment in ways that should, in principle, be detectable. But chemical fingerprints fade over time, becoming progressively harder to distinguish from natural variations, from the background noise of geological processes. Even now, right now as we speak, our own civilization is being written into the geological record in ways that might persist long after we're gone, long after every building has crumbled and every artifact has corroded away. Some researchers call this the Anthropocene, a proposed new geological epoch marked by human influence on the planet, a time interval that future geologists should be able to identify in rock layers. We're leaving plastic in the oceans, microplastics dispersed throughout marine sediments worldwide, tiny fragments that are being incorporated into accumulating layers that will eventually become rock. We're embedding concrete throughout the landscape, creating artificial stone that has a distinctive composition different from natural rock. We're altering the nitrogen cycle through industrial fertilizer production, changing the ratios of nitrogen isotopes in soils and water in ways that affect everything that grows. We've scattered radioactive isotopes through nuclear weapons testing, distributing particular isotopes across the entire globe that will gradually decay but remain detectable for thousands or tens of thousands of years. If future scientists, whoever or whatever they might be, whether human descendants or evolved species or something we can't imagine, dig into the geological layers we're creating right now, they should be able to find these markers. They should be able to identify our time as distinct, unusual, marked by changes that don't match purely natural processes. The question that Schmidt and Frank were asking is, how long would these markers last? How visible would they remain if millions of years passed before anyone looked for them? Would they still be obvious, or would they fade into ambiguity? Would they be clearly artificial, or would they become indistinguishable from natural anomalies? This isn't just idle speculation or thought experiment for its own sake. Thinking this way, asking these questions, helps scientists test the limits of their methods and understand not just what they find, but what they're likely to miss. What might exist but remain undetected because we're not looking for it properly or don't have the tools to recognize it. The geological record is fundamentally, unavoidably full of gaps, of missing information, of periods where we have little or no data. Some periods of Earth's history are well preserved in rock layers that we can access and study. Others are almost entirely erased, removed by erosion, or buried inaccessibly deep or transformed beyond recognition. Erosion can remove entire sedimentary layers that took millions of years to accumulate, erasing vast stretches of time from the accessible record. Tectonic activity can fold and fault and heat and thoroughly scramble entire regions, mixing up the layers, transforming the rocks, making it impossible to read the history they once contained. And then there's the ocean, which covers more than 70% of the planet's surface and hides countless secrets beneath miles of water and sediment, most of which we've never studied in detail, most of which remains essentially unknown. Most of the Earth's surface is geologically young, meaning it's been resurfaced or significantly altered within the last few 100 million years, which sounds like a long time, but is actually less than 10% of Earth's total history. Even the ocean floor gets recycled through the process of subduction, where old oceanic crust is pushed beneath continental plates in convergent boundaries and melted back into the Earth's mantle, completely destroyed, erased as thoroughly as if it had never existed. This means that if an ancient civilization had built anything near ancient coastlines, on islands that have long since been subducted, or in regions that are now part of subducted oceanic crust, those traces would be completely gone, utterly erased, melted back into the planet's interior with no possibility of recovery. And yet here we are now, building and recording and observing, creating our own traces, wondering whether we're alone in the universe, sending messages to the stars, hoping someone will hear. But we rarely ask the more immediate, more unsettling question of whether we've ever truly been alone on this planet, whether we're the first voices to speak here, the first minds to wonder. Maybe the deep past was quieter and emptier than we imagine, truly devoid of intelligence for billions of years until we arrived. Or maybe we've simply lost the ability to hear its whispers, to recognize its signs, to read the faint messages that might be preserved in ways we haven't learned to interpret yet, in languages of chemistry and geology that we're only beginning to understand. Before we go looking for lost civilizations in ancient rock layers and sediment cores, we should probably establish what we're actually looking for, what we mean when we use these loaded terms. What exactly defines a civilization? What characteristics would make something count as such from a scientific perspective? What distinguishes a civilization from just a group of animals living together? These aren't simple questions with obvious answers. They require us to think carefully about what we mean by complexity, by organization, by intelligence itself. In everyday conversation, in casual usage, we tend to think of civilization as an upgraded version of society, something with cities and writing and organized government, perhaps with impressive architecture and technological sophistication. We picture roads and aqueducts, temples and palaces, scripts and books, armies and bureaucracies. But that's actually a quite narrow and culturally specific view that reflects our own historical experience, our own particular developmental path, much more than any universal principle about how intelligence must express itself. Even within human history, when we look across the full diversity of human cultures and societies, civilizations have looked wildly different from one another, expressing similar underlying capacities in remarkably varied ways. Some built vast cities with monuments and extensive road networks connecting different regions. Others left almost nothing behind except patterns of land use and fragments of language and oral traditions. Yet we'd still recognize both as civilizations because what matters isn't any single characteristic, isn't checking particular boxes, but rather a constellation of traits, a pattern of behaviors and capacities that together suggest something more than simple survival. Archaeologists and anthropologists, scholars who spend their careers thinking about these questions, generally identify civilizations by looking for things like urban centers where significant populations concentrate, allowing specialization and division of labor. Specialized labor beyond basic subsistence, people whose full-time work isn't directly producing food, specialists in crafts or governance or ritual. Centralized authority or governance structures, some way of organizing collective action and making decisions that affect the group. Agricultural surplus that supports non-food producing specialists, the economic foundation that allows complexity. Organized religious or ritual practices that suggest shared beliefs and values. Social stratification or hierarchies, differences in power or status or access to resources. Development of symbolic communication or writing systems that allow complex ideas to be preserved and transmitted. And long-distance trade networks that connect different communities and allow exchange of goods and ideas. But even this carefully constructed list has problems. Not all civilizations check all these boxes, and some check them in ways that might not be immediately obvious to outside observers. Some express these traits in forms that anthropologists debated for years before reaching consensus. So when we talk about the possibility of a deeply ancient non-human civilization on Earth, we need to broaden our thinking considerably beyond these human-centric criteria. We're not necessarily looking for pyramids or computer chips, not expecting to find things that match our own technological development. We're looking for evidence of complexity more broadly, of social or technological organization at scales beyond what individual organisms typically achieve, of ecological manipulation that suggests intentionality, things that don't happen by pure accident, patterns that suggest a group of beings organize themselves at scale over extended periods for purposes beyond immediate survival. It's more useful to think about civilization as existing on a spectrum rather than as a binary state you either achieve or don't, rather than as a finish line you cross. Somewhere between isolated survival, individual organisms simply making it through each day, and planetary engineering, civilizations capable of deliberately reshaping entire worlds, there's a vast middle ground of possibilities, a huge space of different ways that intelligence and complexity can express themselves. A culture of tool users that created structures lasting beyond individual lifespans, building things meant to serve future generations. A species that learned to store and transmit knowledge across generations, not just through genetics, but through culture and learning. A group that modified its environment deliberately and systematically, changing landscapes and ecosystems in ways that served their purposes. All of these represent significant evolutionary and cultural developments, major transitions in how life organizes itself and interacts with the world. Consider an example from our own archaeological record, something that challenges our assumptions about what civilization must look like. The ancient settlement of Çatalhöyük in modern Turkey dates back about 9,000 years, making it one of the oldest known urban sites. But it doesn't look like what we typically imagine when we think city. It had no streets in the conventional sense, no open pathways between buildings. It had no monumental architecture, no impressive temples or palaces that dominated the landscape. It had no written language that we've discovered, no inscriptions or texts. Just densely packed homes built directly adjacent to one another, so close that there was no room to walk between them, with inhabitants entering through openings in the roofs and using the roofs as pathways. Yet archaeologists consider it one of the earliest known urban settlements, one of the first places where humans lived in dense concentrations in a town or city-like arrangement. Why? Because what matters isn't the presence of grand structures or familiar urban features, but rather the patterns of coordinated building, the fact that hundreds or thousands of people were organizing their construction efforts, cooperating at large scales. Long-term settlement, people staying in one place across generations rather than moving. With the seasons. Shared ritual practices visible in repeated patterns of decoration and burial. Systematic food production that allowed population concentration. And consistent burial customs that suggest shared beliefs and cultural continuity. Even without impressive skylines or written records, these patterns indicate collective behavior sustained across generations, organization that went beyond what any individual or single family could achieve. That's the signature of something more than just a group of animals living together. It's evidence of culture, of planning, of shared understanding that persisted over time. Go back even further in human prehistory, and the clues become subtler still, harder to recognize, easier to miss. The earliest evidence of symbolic thinking in our species comes from tools that show more refinement than purely functional needs would require, from pigments used for decoration or ritual purposes rather than practical application, from abstract carvings on bone or stone that serve no obvious utilitarian function. These objects imply planning, thinking ahead, considering futures beyond the immediate moment. They imply memory, the ability to hold patterns in mind and reproduce them. They perhaps imply systems of belief, ways of understanding the world that went beyond immediate sensory experience. These aren't technology in our modern sense, aren't computers or engines or complex machinery, but they're technological in their original context, in their time and place. They're evidence that minds were operating in abstract ways, thinking beyond immediate physical needs, considering meaning and beauty and pattern. That's profound. That's significant. That's the kind of thing that leaves traces, though often subtle ones. Now imagine a civilization that existed not 10,000 years ago, but 10 million years ago, or 50 million, or 100 million. What would we expect to find as evidence of its existence? What traces might possibly survive? The answer depends enormously on what that civilization was like, how it lived, what it built with, how it organized itself. If they built primarily with organic materials like wood, plant fibers, animal products, materials that grow and can be harvested without complex processing, those materials wouldn't survive more than a few thousand years under most conditions. Wood rots, fibers decompose, animal products break down. Unless very unusual conditions preserved them, rapidly buried in dry environments, or frozen in ice, or sealed in peat bogs, they'd be completely gone long before millions of years passed. If they buried their dead with elaborate rituals, but without durable grave goods, without metal tools or stone ornaments or ceramic vessels, we might find bones if we were extraordinarily lucky, if conditions happened to be right for fossilization, but we'd completely miss the cultural meaning and sophistication behind the practices, or the ritual and belief and social structure that the burials represented. We'd see bones, if we saw anything, and have no way to understand what they meant to those who buried them. And if they never developed writing, or if they used a form of symbolic communication we wouldn't recognize as writing, something visual or chemical or tactile that doesn't match our expectations, their entire intellectual and cultural history might be irretrievably lost. All their stories, their accumulated knowledge, their understanding of the world, their poetry and history and science, gone without a trace. We think of writing as so fundamental to civilization, but it's actually a relatively recent innovation in human history, and there's no reason to assume it's inevitable or universal. The problem becomes even more severe if this hypothetical civilization didn't live primarily on land. If they were marine, living in and drawing resources from the oceans, or if they spent most of their existence in coastal environments that are now submerged beneath risen seas or subducted beneath continental plates. Coastlines are dynamic, constantly changing. Sea levels rise and fall with ice ages and warm periods. Entire continental shelves that were once dry land are now underwater. And as we discussed, oceanic crust gets recycled relatively quickly in geological terms. Or if they lived in environments that don't preserve fossils or artifacts well, rainforests where humidity and biological activity break down everything rapidly, swampy regions where acidic water dissolves bones and corrodes metal, volcanic regions where periodic eruptions bury everything in ash and lava. Most of the traces would vanish within centuries rather than persisting for millions of years. This isn't a matter of hiding or being secretive or trying to avoid detection. It's simply a matter of the relentless physical and chemical processes of time and geology working against preservation with patient inevitability. We also must be careful, very careful, not to project our own characteristics too strongly onto this hypothetical. We're naturally accustomed to seeing intelligence expressed through spoken and written language, through physical tools that extend our limited bodily capabilities, through manipulation of materials to create structures and devices, through cities and agriculture, and now through digital technology. That's our path, our particular way of being intelligent. But intelligence doesn't necessarily have to look like us or function like us. Evolution can take countless paths to similar capabilities. A civilization might not be industrial at all in any sense we'd recognize, might not extract and process raw materials, might not build with metal or stone. It might organize its society in ways that don't leave substantial material traces, cooperating through biological or chemical signals rather than constructed infrastructure. It might communicate through methods we don't even have conceptual frameworks for understanding. Chemical signaling, like many insects use, but far more sophisticated visual patterns beyond what we can perceive. Acoustic signals in frequency ranges we can't hear, or through forms of behavior and ritual that encode information without requiring written language. This brings up a genuinely strange problem that should make us uncomfortable. Would we even recognize a truly alien form of civilization if we encountered evidence of it? Would our expectations and assumptions blind us to what we were seeing? Think about something like a termite mound as an illustrative example. To human observers, especially casual observers, it appears to be simply a nest, an interesting pile of dirt created by insects. But from an engineering perspective, when you study it carefully, it's actually a marvel of sophisticated architectural and environmental design. These structures feature internal climate control that maintains stable temperatures and humidity despite external fluctuations. They have air circulation systems that manage gas exchange, bringing in oxygen and removing carbon dioxide. They incorporate resource storage areas for food and brood chambers for young. The termites build collectively, coordinating their activities through chemical signals despite having no central planning or conscious understanding of what they're creating. They farm fungus for food, cultivating it deliberately. Their colony behaves in many ways as a single superorganism, individual termites like cells in a body. If we didn't have living termites to observe and study, if we only found their fossilized mounds millions of years after the insects were extinct, would we recognize what we were seeing? Would we understand that these structures represented sophisticated collective behavior? Or would we classify them as interesting geological formations, curious but natural? Without context, without the living behavior to observe, interpretation becomes extraordinarily difficult. Scale that problem up by many orders of magnitude, bury it for millions of years with all the distortion and transformation that entails, and even more obvious traces of intelligence might become indistinguishable from natural formations. A deliberately constructed structure, if weathered and partially destroyed and buried and compressed and heated, might look like a natural rock formation. Regular patterns might be attributed to crystal growth or geological processes. Chemical anomalies might be explained by volcanism or hydrothermal activity. So when we contemplate lost civilizations, we need to think like archaeologists and biologists simultaneously, bringing both perspectives to bear on the question. We're not just looking for ruins in the traditional sense. We're looking for patterns, for anomalies, for disruptions in what we'd expect to find based purely on natural processes. Unexpected concentrations of certain minerals that suggest extraction or processing. Changes in sediment composition or layering that don't match known geological processes. Unusual isotope ratios in rock layers that indicate chemical activity of types we don't expect. Things that might suggest someone or something was doing something unusual, something purposeful at a particular place and time. There's also the crucial question of duration and intensity. How long would a civilization have to exist, and how intensively would it have to impact its environment to leave a mark detectable millions of years later? Interestingly, not very long in geological terms. Humans have transformed the entire planet in just a few hundred years of industrial activity, a duration so brief it would be barely visible in rock layers, compressed to perhaps a few centimeters of sediment. Yet the chemical impact is measurable, significant, global. Greenhouse gases altering atmospheric composition. Synthetic compounds that never existed before, spreading worldwide. Nuclear isotopes scattered across the entire planet from weapons testing. Even if industrial civilization vanished tomorrow, some of those changes would still be detectable for tens of thousands of years, possibly millions of years in the right preservation conditions. The layer marking our time might be thin, but it would be chemically distinctive, anomalous, strange, compared to what came before and presumably what would come after. So maybe the better question isn't simply whether a previous civilization existed, but whether we're even asking the right questions to detect one, whether we're looking in the right places with the right tools and the right expectations. We naturally look for signs that make sense to us: fossils of biological organisms, ruins of buildings, tools that match our understanding of technology. But what if the signs are stranger than we expect, smaller than we're looking for, or in places and forms we haven't thought to investigate? What if they're chemical rather than physical, subtle rather than obvious, ambiguous rather than clear? When people hear the word fossil, they typically picture a perfectly preserved dinosaur skeleton dramatically displayed in a museum, every bone in place, arranged in lifelike poses as though the creature simply lay down one day and transformed smoothly into stone. But real fossils, actual fossils, rarely look anything like that idealized, sanitized image we carry in our minds. They're usually fragmentary, just pieces rather than complete specimens. They're partial, missing most of the original organism. They're compressed, flattened by the weight of overlying sediments. They're distorted, bent and twisted by geological forces. They're incomplete, with soft tissues almost never preserved and even hard parts often missing. Real fossilization requires extraordinary luck, a cascade of improbable events, a precise sequence of very specific environmental conditions, all occurring in the right order. Even under optimal circumstances, even in environments that favor preservation, fossilization is the rare exception rather than the expected norm. It's exceptional, unusual, remarkable when it happens. And importantly, crucially for our inquiry, the story fossils tell is often incomplete, selective, biased towards certain types of organisms in certain types of environments, and silent on many crucial details. The fossil record represents one of our best tools, perhaps our very best tool, for understanding ancient life, for reconstructing ecosystems and evolutionary processes and the history of life on Earth over hundreds of millions of years. But it emphatically does not give us a complete or fully representative picture. It's not comprehensive. It's more like trying to reconstruct an entire movie, a complex narrative with plot and character and theme, from just a handful of random still frames, some torn and faded pieces of film showing only fragments of scenes, and a few scattered subtitles in languages you only partly understand and can't always translate accurately. For every species we've successfully identified in the fossil record, for every organism we've found and named and studied, there are likely dozens or hundreds or perhaps thousands of others that left absolutely no trace. Some never fossilized in the first place, their remains destroyed before preservation could occur. Some did fossilize, but those remains were subsequently destroyed by geological processes, heated and melted, or crushed and deformed beyond recognition, or eroded away and scattered. Still others lie buried in sediments we haven't explored yet, in regions that are inaccessible or unexplored, or in rock layers that haven't been exposed at the surface where we could find them. This inherent incompleteness of the fossil record is crucial to keep in mind, absolutely essential to remember as we contemplate ancient civilizations, especially hypothetical, non-human ones. We're already working with a record that's full of significant blind spots, massive gaps, even when we're looking for relatively common organisms that lived in environments favorable to fossilization. Fossilization depends on an improbable combination of factors all aligning correctly, a perfect storm of fortunate circumstances. It matters enormously how an organism dies. A creature that dies and falls into a river getting swept along and torn apart by current and rocks, has little chance of preservation. One that dies in a calm lake or lagoon and settles into fine-grained sediment has a much better chance. It matters where the death occurs. Deep ocean environments with slow sedimentation often preserve nothing. Shallow marine environments with active burial sometimes preserve beautifully. Terrestrial environments are generally poor for fossilization because remains are exposed to weathering and scavengers. It matters what kind of sediment buries the remains. Fine-grained mud can preserve delicate details. Coarse sand often destroys them. It matters how quickly burial occurs. Rapid burial by flood or volcanic ash protects remains from scavengers and decay. Slow burial allows destruction. It matters whether scavengers or decomposers get access to the body before it's sealed away. A few days' exposure can mean the difference between preservation and complete loss. It matters whether the burial site remains geologically stable. Tectonic activity can heat, compress, fold, and deform rocks, destroying fossils in the process. Volcanic activity can melt them. Erosion can expose and destroy them. It matters whether erosion or tectonic activity later exposes the fossil in a way that doesn't destroy it in the process, which is actually quite rare. Many fossils are probably eroded away before anyone finds them, or remain buried where we'll never access them. Now imagine trying to preserve not just biological remains like bones and shells, which are already challenging, but cultural artifacts, manufactured tools, constructed buildings, technological infrastructure, things that don't even begin with the relative durability of mineralized bone or calcium carbonate shell. The odds drop precipitously, falling to levels that make preservation seem almost miraculous when it occurs. Even stone tools, which are among the most resilient of human artifacts, can be difficult to date accurately and even to identify as artificial if they're found out of their original context, without associated materials or clear patterns of use. A chipped and broken rock might be a deliberately manufactured tool, carefully shaped by skilled hands. Or it might be just a naturally fractured rock, broken by geological processes or thermal stress. Without clear patterns of repeated use visible as wear marks, without associated artifacts that provide context, without other evidence of human or intelligent presence, it becomes genuinely difficult to make definitive determinations. Archaeologists sometimes debate for years whether particular objects are tools or natural formations. Most technological materials, most of what civilizations make, don't survive anywhere near as well as stone or mineralized bone. Metal corrodes relatively quickly when exposed to oxygen and moisture, essentially returning to the oxidized ores they were originally extracted from. Iron rusts, turning back into iron oxide. Copper oxidizes, forming green patinas that gradually weather away. Bronze corrodes. Steel rusts even faster than pure iron. Even specialized alloys designed to resist corrosion eventually fail. Fabric, leather, wood, and other organic materials decompose unless buried in highly unusual environments that lack oxygen or moisture. Underwater in low oxygen conditions, frozen in permafrost, sealed in very dry caves, preserved in peat bogs. These special environments are rare, covering tiny fractions of Earth's surface. Most organic materials simply rot, broken down by bacteria and fungi and insects within years or decades. Plastic, despite its reputation for persistence, its stigma as an eternal pollutant, actually breaks down fairly readily when exposed to ultraviolet light from the sun and to microbial action, fragmenting into progressively smaller pieces. Unless it's sealed away in oxygen-free conditions, protected from sunlight and biological activity, plastic degrades over centuries or millennia into microplastic particles and eventually into molecules that disperse. This means that even for our own relatively recent ancestors, even for humans who lived just thousands of years ago, The archaeological record is frustratingly incomplete, maddeningly partial. We have gaps, silences, mysteries that we'll never solve because the evidence simply doesn't exist anymore. Consider Homo erectus as a specific example, a particular species we can examine. This human ancestor existed for nearly 2 million years across much of the Old World, from Africa through Asia, adapting to diverse environments. 2 million years. That's an immensely successful run for any species, especially a large mammal. We have evidence of their stone tools, sometimes in great quantities at particular sites. We have occasional bones that happen to be buried in the right conditions, though they're rare relative to how many individuals must have lived. We have indications that they used fire, traces of ancient hearths, and burned materials. We have evidence of relatively sophisticated behaviours, planning and cooperation, and adaptation. But vast aspects of what they did and how they lived remain fundamentally unknown to us, lost forever. They travelled widely across continents, covering thousands of miles, adapting successfully to different climates and environments from tropical forests to temperate woodlands. They almost certainly had some forms of communication, ways of sharing information, and coordinating activities that went beyond simple instinct. They may have had early forms of language, though we have no way to recover what they might have said. We don't know what they believed, whether they had concepts of spirituality or meaning beyond survival. We don't know how complex their social structures were, whether they had leaders or hierarchies or egalitarian arrangements. We don't know what they might have dreamed about, what they hoped for, what they feared beyond immediate threats. We don't have their thoughts, their subjective experiences, their individual personalities and relationships, not because they didn't have these things, but because such aspects of life don't fossilize, don't leave traces that survive hundreds of thousands or millions of years. And this is for our own species. For humans, for remains that are only thousands or tens of thousands, or at most a couple million years old, not tens or hundreds of millions. We're talking about organisms we're directly related to, whose bodies were similar to ours, whose behaviours we can partly understand through analogy. And yet we still have huge gaps in our knowledge. If we have this much trouble, these many mysteries, in reconstructing the lives of our own ancestors from such geologically recent times, how could we possibly expect to find clear, unambiguous evidence of a completely different species, perhaps radically different from us in form and function, that lived tens or hundreds of millions of years earlier? The honest answer, the answer that humility and scientific understanding compel us toward, is that we probably couldn't, not unless they left something truly exceptional, something that managed to survive against extraordinary odds. This brings us to an important realization about what kinds of evidence might actually persist from a hypothetical ancient civilization, what might possibly survive the gauntlet of deep time. If we were looking for signs of a past intelligent species, we might find them only if that species lived in or near one of the relatively rare environments that promote fossilization, and even then only if they were caught in some kind of preservation-friendly catastrophe that buried evidence quickly before decay and scavenging and weathering could destroy it. It's an extraordinarily narrow window of possibility, a tiny target in the vast space of what could have happened. There's also a more subtle issue to consider, one that's almost philosophical but has real practical implications. What if a civilization had advanced to a point where it stopped leaving traditional biological remains entirely? What if they had developed technologies for life extension, or for uploading consciousness into non-biological substrates, for transferring minds into silicon or quantum computers, or forms of matter we haven't discovered? What if they transformed themselves into something that wasn't dependent on organic bodies, that didn't die and decay in conventional ways? We genuinely don't know whether such things are possible. They might violate physical laws we don't fully understand yet. They might be pure fantasy, forever impossible. But if they were possible, if some civilization managed such transformations, the fossil record wouldn't just be incomplete. It would be entirely irrelevant to understanding their existence, completely useless for detecting them. Even in our current era, right now, most of the material involved in our daily technological lives is synthetic, non-organic, or so heavily processed that it wouldn't register as straightforwardly biological to someone studying our remains millions of years hence. A future geologist drilling core samples through rock layers corresponding to our time might discover thin layers containing strange polymer compounds with no natural analogues, unusual concentrations of rare earth elements in patterns that don't match any known ore deposits, novel metal alloys with precisely controlled compositions that never occur naturally through geological processes. They might not immediately recognize these as remnants of a technologically sophisticated civilization, especially if broader context is missing, especially if they find just isolated anomalies without connecting patterns. They might categorize them as interesting chemical oddities, unusual but perhaps within the range of natural variation, unexplained but not necessarily artificial. Interpretation requires context, requires patterns, requires enough data points to distinguish signal from noise. This is why the Silurian hypothesis that Schmidt and Frank proposed, that we discussed earlier, focuses not primarily on finding fossils or physical artifacts, but rather on looking for chemical signatures, for changes in the geochemistry of rocks and sediments that might indicate industrial or technological activity. Modern industrial civilization is definitely, unambiguously, leaving clear chemical fingerprints that should persist for substantial periods. Changes in carbon isotope ratios from burning fossil fuels, because fossil fuels have distinctive isotopic signatures. Introduction of synthetic organic compounds that don't occur naturally through any known process. Elevation of heavy metal concentrations in soils and sediments. Radioactive isotopes from nuclear testing that will decay gradually but remain detectable for thousands of years. If an earlier civilization had engaged in similar activities, had burned fuels or manufactured synthetic compounds, or concentrated particular elements, or generated radioactive materials, those chemical fingerprints might potentially survive in the rock record even when physical artifacts have long since completely vanished, even when every building and tool has been destroyed. Chemistry can be more durable than structure, molecules more persistent than monuments, but even chemical signatures present serious interpretation challenges that can't be dismissed. Nature produces its own extraordinarily complex geochemical signals through volcanic activity that releases gases and elements, through biological processes that cycle nutrients and transform compounds, through interactions between atmosphere and ocean and rock that create chemical gradients and concentrations. The Earth's natural chemistry is rich, varied, complex, and constantly changing. Distinguishing artificial chemical patterns from natural ones requires not just detecting an anomaly, not just finding something unusual, but building a compelling case that the anomaly couldn't have been produced by any known natural process, that it requires technological explanation. And that's a genuinely high bar to clear, as it should be in science. Extraordinary claims do genuinely require extraordinary evidence, and the burden of proof for proposing ancient civilizations is appropriately heavy. If tomorrow, at some precisely defined moment, every human being vanished from Earth without warning, without explanation, without disaster or gradual decline, just gone instantaneously, what would the world look like a year from now? A century? A millennium? A million years? This grim but illuminating thought experiment, this exercise in imagining our absence, helps us understand concretely what kind of trace a civilization actually leaves behind, and, more importantly for our purposes, how long any of those traces might persist in the geological record. It gives us a framework, a concrete way to think about what we should look for if we're searching for evidence of civilizations that might have existed in the deep past. What signatures would be durable enough to survive deep time? In the immediate aftermath of human disappearance, in the first days and weeks, not much would change visibly on the surface. Cities would still stand with their buildings intact, solid, and seemingly permanent. Streets would remain clear, marked by painted lines and traffic signals frozen in their last configuration. Vehicles would sit motionless wherever they were last parked or driven, keys perhaps still in ignitions. Infrastructure would still exist in recognizable form, bridges spanning rivers, power lines stretching across landscapes. But very quickly, faster than most people intuitively expect, without constant human maintenance and oversight, the systems that support our technological civilization would begin failing in cascading sequences. Power plants would shut down within hours or days as automated safety systems responded to the absence of human operators. Fuel supplies depleted, cooling systems failed. The electrical grid would go dark section by section as power plants went offline and automated systems couldn't coordinate to maintain stability. Water treatment and distribution systems would lose pressure and cease functioning within days. Pipes draining, treatment plants flooding or running dry. Sewage systems would back up or overflow. Without electricity and active management, without constant monitoring and adjustment, the complex web of infrastructure we depend on without thinking would start to unravel. Systems designed for human supervision failing in the absence of that supervision. Within just a few years, remarkably quickly, nature would begin aggressively reclaiming our cities, moving into spaces we had cleared and controlled. Plant seeds, carried by wind and birds and water, would find purchase in cracks in pavement, in gutters clogged with leaves, in soil accumulated on rooftops. Roots would begin lifting sidewalks and breaking through foundations, leveraging their growth with surprising force. Trees would sprout in parks and yards and eventually in streets where soil had accumulated. Animals would return to areas we had dominated, and not just adaptable species like rodents and birds and raccoons that already share our spaces. Increasingly larger creatures would move in, deer wandering through suburban streets, predators following their prey into cities, entire ecosystems gradually re-establishing themselves in spaces we had cleared and controlled for centuries. In wetter climates especially, the boundary between built environment and wild nature would blur remarkably quickly, within decades rather than centuries. In urban centres like New York or Tokyo or Sao Paulo, subway systems and underground infrastructure would flood within days once the pumps that constantly remove groundwater stopped operating. These systems exist below the water table in many cities, kept dry only through constant pumping. Without that, water would rise, flooding tunnels and stations, corroding electrical systems and structural elements. Steel structural elements, the bones of modern buildings, would begin to rust, a process accelerated dramatically by exposure to moisture and oxygen. In coastal cities, salt spray would accelerate corrosion even faster. Glass windows would gradually shatter from thermal stress, from shifting foundations, from objects blown by wind. Without the careful climate control that keeps temperatures stable, glass expands and contracts with temperature changes, creating stresses that eventually lead to fractures. Concrete, despite seeming exceptionally durable, despite being the foundational material of modern construction, is actually vulnerable to moisture infiltration and temperature cycling. Water seeps into tiny cracks and pores. When it freezes, it expands, forcing cracks wider. When it thaws, it allows deeper penetration. Over cycles of freezing and thawing, of wetting and drying, concrete degrades. Steel reinforcing bars, rebar, inside concrete expand as they corrode, creating internal stresses that crack and break apart the concrete from within, a process called concrete cancer by engineers. Within decades, just a few human lifetimes, many buildings would begin collapsing under their own weight, especially in regions with significant rainfall or freeze-thaw cycles. Roofs would fail first, allowing water and snow to enter. Interior floors would rot or collapse. Eventually, outer walls would fail, and entire structures would come down in progressive collapses, floor by floor. Roads and highways would deteriorate more slowly than buildings, but still surprisingly fast. Vegetation would tear through asphalt surfaces, roots finding any tiny crack and exploiting it. Tree roots are particularly effective at breaking up pavement, growing with steady pressure that nothing artificial can match. Without maintenance to clear drainage systems and repair small damages before they propagate, water would pool and accelerate the breakdown of road surfaces through the same freeze-thaw cycles that destroy buildings. Bridges, lacking regular inspection, paint maintenance to prevent rust and structural repairs, would gradually weaken and eventually collapse. Support structures would corrode. Cable suspension bridges would see cables fray and snap. Arch bridges would see mortar deteriorate. Eventually, whether through sudden collapse or gradual sagging failure, almost all bridges would fall, their spans dropping into the rivers and canyons they once crossed. Satellites orbiting Earth would start failing as their batteries degraded, as solar panels accumulated damage from micrometeorite impacts and radiation, as electronic components failed from accumulated radiation exposure. Most satellites in low Earth orbit, the crowded region a few hundred kilometers up where most satellites operate, would deorbit and burn up in the atmosphere within a few centuries, their orbits decaying due to drag from the extremely thin upper atmosphere. Only those in very high orbits, in geosynchronous orbit or beyond, would persist longer, though they too would slowly, inexorably decay and eventually spiral inward over geological timescales measured in millions of years. After about 1,000 years, just a single millennium, much of what currently defines human presence on Earth would already be unrecognizable, already difficult to identify as artificial. Steel structures would have collapsed into rust-stained heaps, oxide minerals scattered across what were once building sites. Plastics exposed to sunlight would have degraded into progressively smaller fragments through photodegradation, UV radiation breaking chemical bonds. Underground infrastructure like cables, pipes and tunnels would have corroded significantly, though some protected elements might remain recognizable. The outlines of cities might still be faintly visible from aerial perspectives, especially in drier climates where decay proceeds more slowly, where lack of moisture limits biological activity, and freeze-thaw cycles. Patterns of streets and building foundations might create subtle differences in vegetation or soil that could be detected from above, but they would resemble faint scars on the landscape, shadows of former patterns rather than recognizable urban centers. 10,000 years into this scenario, a span that takes us back to the dawn of agriculture in human history, even those faint scars would be fading rapidly in most environments. Forests would have completely reclaimed temperate zones, trees growing undisturbed for hundreds of generations. Deserts would shift and migrate in response to climate patterns, potentially burying entire cities under sand dunes. Coastlines might look very different due to ongoing erosion, sedimentation, and possibly sea level changes from climate effects already set in motion during our time. What survives at this point would depend heavily on local conditions and the specific materials involved. Stone monuments and carvings, especially those of solid rock rather than assembled blocks, might persist much longer than other structures. Consider something like Mount Rushmore, carved faces in solid granite, or the pyramids of Giza, massive structures of carefully fitted stone blocks. These might remain recognizable for tens of thousands of years, possibly even 100,000 years if geological activity doesn't destroy them first. But most modern infrastructure, built with steel and concrete and designed for function rather than multi-millennial permanence, wouldn't make it nearly that long. Modern buildings, bridges, dams, all would be gone or unrecognizable, reduced to scattered rubble that might not obviously be artificial. Extend the timeline further to 100,000 years, and almost every surface structure would be completely gone, erased by weather and biological activity. Only the deepest foundations, buried structures protected from weathering, the most stable landfills sealed away from oxygen and water, and certain large-scale geological modifications like open-pit mines, quarries, and dramatically altered sediment layers might still be detectable to someone who knew what to look for and where to look. But even these would be weathered, filled in by natural processes, or buried under accumulating sediment. Any meaning or purpose they once held would be utterly lost unless somehow encoded in patterns or materials that could be deciphered without cultural context, which seems nearly impossible. A rectangular foundation might be natural or artificial. A concentration of minerals might be an ore deposit or the remains of industrial waste. Without context, interpretation becomes speculation. Now push the timeline to 1 million years, finally reaching the scale we've been discussing throughout this exploration. What would survive of human civilization after that truly immense span, after 40,000 human generations, after a period longer than our species has existed? The honest answer, the answer that geology and our understanding of Earth's processes compel us toward, is not very much in terms of physical structures or recognizable artifacts. Perhaps a few items in exceptionally stable, dry environments might persist. Objects sealed in caves in arid regions, materials buried deep underground in geologically stable zones, possibly some materials in polar ice, though even ice eventually flows and sublimes over such timescales. Perhaps some synthetic molecules that strongly resist chemical breakdown might survive in certain environments. Perhaps distinctive layers in lake beds or ocean sediments showing characteristic spikes in carbon concentrations, unusual patterns in nitrogen or phosphorus indicating agricultural activity, plastic residues, or rare earth metal concentrations suggesting industrial processing. These chemical signals, these molecular fingerprints, would be the real fossils of civilization, not buildings or books or art, but geochemical echoes of industrial and agricultural activity, subtle changes in planetary chemistry. Not monuments intended to last, but molecular markers left accidentally. If our civilization disappeared tomorrow, the planet would begin erasing us almost immediately, not through any deliberate action or cosmic malice, but simply through the mechanical operation of geological and biological processes that have operated throughout Earth's history. Erosion would begin wearing away exposed structures. Chemical weathering would dissolve and transform materials. Biological decay would break down organic compounds. And plate tectonics would continue its slow but relentless work, subducting oceanic crust, building mountains, opening ocean basins, constantly renewing and transforming the surface. These processes would continue their work without interruption, without pause, without regard for what we built or what we meant to preserve. And over time, gradually but inevitably, the evidence that we had ever existed would become progressively harder to prove definitively, harder to distinguish from natural variation, harder to interpret without context. The traces would fade like a photograph left in sunlight, losing definition and detail until only the faintest pattern remained. This realization isn't merely philosophical or speculative. It's absolutely central to our question about lost civilizations, fundamental to how we approach the possibility. Because if our own civilization, with all its global reach and technological intensity and massive infrastructure and billions of people, could be erased so thoroughly over geological timescales, then how could we expect the traces of any earlier civilization to have fared any better? What makes us think our predecessors, if they existed, would have left more durable marks than we will? It also gives us a practical benchmark for investigation, a standard for what to look for. If any part of us can persist through deep time, if anything at all leaves a truly durable global signature that survives millions of years of geological processing, then perhaps those are precisely the kinds of markers we should be searching for when we ask whether we were the first intelligent species on Earth. Not pyramids, but chemistry. Not monuments, but molecules. Not ruins, but ratios of isotopes in ancient rocks. What would survive of us wouldn't be the things we built with conscious intention to last, the monuments and museums and cathedrals meant to commemorate and preserve. Those would be among the first to go, exposed to weathering, vulnerable to geological forces. Instead, what persists would be our wastes, our byproducts, our accidental transformations of planetary chemistry, the things we never meant to leave behind. The carbon dioxide we released into the atmosphere by burning hundreds of millions of years of accumulated fossil fuels in just a few centuries. The nitrogen we fixed industrially through the Haber-Bosch process, doubling the amount of reactive nitrogen in the biosphere. The radioactive isotopes scattered worldwide by nuclear weapons testing, creating a global marker layer. The mass extinction we triggered through habitat destruction and climate change, a sharp drop in biodiversity visible in the fossil record. The redistribution of biomass and chemical elements across the planet through agriculture and industry. These aren't structures or artifacts in any traditional sense. They're planetary modifications, fundamental changes to biogeochemical cycles that operated in relative stability for millions of years before we came along, and they're considerably harder to erase completely than any building because they're dispersed globally, incorporated into systems, embedded in the functioning of the planet itself. So imagine now that you're a geologist millions of years in our future, living in a world transformed beyond anything we could recognize, carefully examining a cylindrical core sample drilled from ancient sedimentary rock laid down during our time. You notice a thin but distinctive layer, just a few centimeters thick, representing perhaps a few thousand years, characterized by several unusual features. Elevated carbon concentrations and a shift in carbon isotope ratios consistent with massive fossil fuel combustion. Unusual isotope ratios in nitrogen suggesting industrial fixation. A sharp drop in the diversity of fossil pollen indicating mass deforestation and extinction of plant species. Traces of synthetic chemical compounds that don't match any known natural process. Perhaps even traces of plutonium or other isotopes that clearly indicate nuclear fission, something that doesn't happen naturally on Earth's surface. You might reasonably ask, confronting this data, what happened during this period? What caused these correlated anomalies? Was this purely natural, some combination of volcanism and asteroids? Impact and climate fluctuation that coincidentally produced these patterns? Or was something else involved, something that manipulated chemistry and transformed ecosystems on a global scale? That's where our thought experiment leads us, to this moment of interpretation and uncertainty. By imagining our own disappearance and what traces we'd leave behind, we gain clearer, more concrete insight into what kinds of evidence actually endure at geological timescales, what would rise to the level of a detectable planetary signal that couldn't be easily dismissed, and what would simply vanish into the background noise of natural variation. The challenge then becomes one of recognition and interpretation, because even if we leave a detectable mark, even if our chemical fingerprints survive in rock layers, the real difficulty lies in ensuring that future investigators recognize it for what it actually represents, that they don't attribute it to natural causes, that they make the inferential leap from anomaly to intelligence. And that leap is difficult, requiring not just data but framework, not just observation but theory that makes sense of what's observed. When people talk romantically about cities lost to the sea, the names that come up first are usually mythical. Atlantis with its advanced technology and moral downfall, Lemuria as a proposed lost continent in the Indian Ocean, Lyonesse off the coast of Cornwall in Arthurian legend. These are myths, stories passed down and embellished and repurposed by fiction and fantasy and nationalist folklore. But the real ocean, the actual physical ocean covering most of our planet, has been swallowing real cities, actual human settlements, for a very long time. And importantly, crucially, not one of them left behind anything close to intact monuments under the waves. The sea doesn't preserve secrets carefully like a museum curator. It breaks them down. It dismantles them. It works slowly, but it doesn't stop, never pauses, never rests. When a city or settlement falls into the ocean, whether through rising sea levels or subsiding land or catastrophic events, what remains after a few thousand years, let alone a few million, isn't stone columns standing sentinel in the depths, or mosaic floors preserved pristine beneath sand. It's silence and rubble and ambiguity. It's formations that might be walls or might be natural rock. It's regular shapes that might be foundations or might be geological structures. It's mystery and interpretation and often disagreement about what's being seen. Coastal regions have always drawn civilizations, drawn them with powerful incentives that are easy to understand. Fertile land in river deltas, easy access to trade by water, cheaper and faster than overland transport for most of human history. Predictable weather patterns moderated by proximity to large water bodies. Access to marine resources, fish and shellfish and seaweed. These are the conditions under which complexity tends to form, where surplus allows specialization, where trade enables cultural exchange. And yet, by building on the coast, you're also building on a boundary, on a frontier between stability and motion, on a transition zone that shifts constantly. Coastlines aren't fixed features of geography. They migrate with tides daily, with seasons, with storms, with earthquakes that raise or lower land, with the long, slow breathing of glacial cycles that lock water in ice sheets or release it to the oceans. Sea levels rise and fall by hundreds of feet over tens of thousands of years. Land itself lifts through tectonic processes or sinks through subsidence. What is now dry land might have been seabed 50,000 years ago, and what is seabed today might have been inhabited land before the ocean came for it, before the waters rose and swallowed settlements that had stood for generations. Take Dwarka, a site off the western coast of India in the Gulf of Khambat, often cited in alternative history circles as one of the oldest underwater urban ruins ever found, potentially dating back thousands of years before conventional histories of Indian civilization. Some structures discovered there appear to show signs of deliberate construction, regular shapes, and patterns that don't obviously match natural formations. But the exact nature of the site remains hotly debated among archaeologists and geologists. Erosion has modified whatever is there. Biological growth, corals and algae and barnacles has covered surfaces. Sedimentation has buried portions. And interpretation depends heavily on what you expect to find, what you're looking for, what framework you bring to the evidence. Other examples exist around the world, fragmentary hints of human presence now underwater. Pavlopetri off the southern coast of Greece, submerged around 5,000 years ago, shows remains of buildings and streets but heavily eroded, difficult to interpret in detail. Parts of the Doggerland region in the North Sea, once inhabited during the last ice age when sea levels were much lower, now yields occasional artifacts when fishing nets drag across the bottom, but the settlements themselves are buried under meters of sediment, effectively inaccessible for detailed study. In each case, without exception, traces are faint, fragmentary, difficult to interpret with confidence. They're found not because they're well preserved in any conventional sense, but because they're close in distance and time, shallow enough to access with current technology, and recent enough that some structures remain recognizable. Go further back in time, push the timeline deeper, and the ocean doesn't just bury evidence passively. It actively erases, breaks down, transforms, recycles. The seafloor is constantly being reshaped by processes most people never think about. Currents, some slow and steady, some fast and powerful, redistribute sediment across vast areas. Marine organisms colonize and transform any exposed surfaces, boring organisms creating holes, encrusting organisms covering everything with layers of shell and calcium carbonate, burrowing organisms mixing sediments and destroying stratification. Corrosion eats away at exposed metal and concrete, salt water being particularly aggressive at breaking down materials we consider durable on land. And most importantly, most relentlessly, new layers are always being added, sediment constantly raining down from above, gradually burying whatever exists below. Anything that isn't buried quickly and deeply enough, anything that remains exposed to water and biological activity, gets broken down by combined chemical, mechanical, and biological processes. Stone surfaces become roughened and pitted. Mortar between blocks dissolves. Metals corrode into oxide minerals and disperse. Wood, if any survived initial decay, becomes waterlogged and collapses or is consumed by marine borers. This is why submerged cities don't look like cities for long, don't remain recognizable across even modest timescales. Even stone structures, built to last on land, can't withstand indefinitely the combined effects of salt water, wave energy, current action, and what marine biologists call bioerosion, the gradual destruction of materials by living organisms. Over centuries and millennia, not millions of years but just thousands, corners round off and lose their sharpness. Carvings and inscriptions fade into illegibility. Mortar and cement dissolve completely. Organic material disappears entirely, leaving no trace. Over time, anything man-made on the seafloor becomes unrecognizable. Walls crumble into ridges, buildings collapse into piles that look like rockfalls, and any straight edges get mistaken for natural formations. And that's for structures only a few thousand years old, things we at least understand. If something sank 10 million years ago, during the time of dinosaurs or early mammals, the ocean would have erased it completely. Marine life would break it down, currents would scatter it, and sediments would bury the remains until they blended into the seabed. Even if traces still exist, we've barely explored the ocean floor. We've mapped the Moon and Mars in more detail than the deep sea. Sonar only shows general shapes. Submersibles cover tiny areas and are expensive. Most of the seafloor hasn't been examined closely enough to spot anything buried or eroded. Scientists study sediment cores to read Earth's past, ash layers from eruptions, iridium from asteroid impacts, chemical shifts from climate events. Once in a while, they find a strange chemical spike or odd isotope ratio that doesn't fit expectations, but none have been tied to ancient civilizations. Maybe we don't yet know how to interpret the signs. If a past society polluted oceans, built coasts, or altered ecosystems, the traces would have to be huge and rapid to stand out from natural changes. Look at Fukushima in 2011. Radioactive isotopes entered the Pacific immediately and spread across oceans within years. Now imagine trying to detect something like that 50 million years later, with no records, decayed isotopes, and only scattered chemical hints. Any anomaly could just as easily be volcanic activity or cosmic rays. Without proof of artificial origin, science defaults to natural explanations. The ocean isn't a museum, it's a recycling system, It destroys, buries, and transforms. Cities don't sit intact underwater. They dissolve, break apart, and vanish into sediment. If something leaves no trace, can we prove it existed at all? Probably not in any hard geological sense. Yet sunken regions still remind us how fast complexity disappears. They warn us how fragile human marks are. Layered rock tells stories, but only those nature preserves. Climate shifts, eruptions, extinctions. Sometimes anomalies appear, odd minerals, strange isotopes, fossils in the wrong place. But most are later explained. A few remain unresolved, but not confirmed artificial. People have long claimed artifacts inside coal or mysterious metal spheres in ancient rock. Most are misidentifications, contamination, or natural formations. Science treats anomalies cautiously, asking if familiar processes can explain them before considering anything extraordinary. Some of the best evidence, if it existed, wouldn't be objects but chemical signals, unnatural isotope ratios, synthetic molecules, rare metals in global layers. We haven't found anything like that, or if we have, it sits overlooked in data labelled unusual. Big discoveries often came from reinterpreting old evidence with new ideas. Maybe no past civilization existed. Maybe intelligence is rare and we're first. Or maybe others rose and vanished without leaving permanent evidence, wiped away by oceans and time. Without stone or metal, only chemistry might remember them. Wondering about this is part of being conscious, reaching through time, asking who came before. Not to expect Atlantis, but to stay open to mysteries written in rock and water. Whether we're alone in history or not, the act of asking connects us to something much bigger. Good night, traveller. The past will wait, the future will come, and for now, rest is enough.